Have you ever really stopped to think about how medicines, these really precise things we take, actually manage to get exactly where they need to go inside us?
Yeah, it's a huge challenge, right?
Totally. You want the drug hitting the right spot, doing its job precisely, not just flooding your whole system with stuff it doesn't need everywhere else.
Mm-hmm.
It's like trying to deliver a tiny, super specialized package to one specific apartment in a massive skyscraper,
Right.
without ringing every single doorbell.
That's a really good way to put it.
Yeah.
And yeah, traditional pills or injections, they often just don't give you that pinpoint accuracy.
Right.
And that's where innovation kicks in.
Yeah.
Today, we're doing a deep dive into something really fascinating that addresses this. Organogels.
Organogels. Okay, that sounds pretty high tech. What exactly are they? How do they work this magic?
Well, basically, they're semi-solid formulations. So imagine this really delicate, intricate sort of scaffold
Okay.
that hold an oily or, a non-watery liquid completely still. It stops it from flowing.
An oily phase, right?
Exactly, in a polar phase.
Yeah.
And it's immobilized,
Yeah.
trapped within this 3D network structure.
Gotcha. And our deep dive today, it's digging into a big review article from Design Monomers and Polymers.
That's the one. It really explores the properties, the applications of these organogels, especially, like we said, for drug delivery.
So our mission then is to unpack what they are, how they pull off this precise control, what makes them tick.
Their key characteristics, yeah. And where they're already being used, where they might go next, all for you, the listener.
Okay, let's get into it. So we have this scaffold holding this oily liquid. Who are the architects? What actually builds the structure?
The architects, they're called gelators.
Gelators.
Yeah, these are special compounds, molecules really, that self-assemble. They just kind of click together on their own, almost like tiny Lego bricks. And they form these really complex networks. What's amazing is they do this at surprisingly low concentrations. We're talking typically less than 15% of the whole mix.
Wow, less than 15%. That's incredibly efficient.
It is. A tiny bit of gelator goes a very long way.
So these self-assembled structures, they tangle up and create this network that stops the oily phase from flowing. What makes them so stable once they're formed? Like, why don't they just fall apart?
Well, what's really neat is that they are thermodynamically stable, meaning they naturally settle into a low-energy state. They're quite happy just being gels. It's their preferred state, energetically speaking.
Ah, okay.
And that inherent stability, it's a massive advantage for things like shelf life, especially for pharmaceuticals, right?
Yeah.
Things that need to last.
Right, so they won't suddenly collapse on the pharmacy shelf. And they have some other interesting traits, too. You mentioned thermoreversible.
Exactly, thermoreversible. So they can change from that gel state to a liquid state if you heat them up.
Okay.
And then they solidify right back into a gel when you cool them down again. They're also sensitive to moisture. And both these things, the heat response and the moisture response, are being looked at really closely for creating super precise, controlled drug delivery systems.
And the gelators themselves, they come from some common things.
Yeah, some are derived from things like sterols, lecithin, even some specialized cholesterol derivatives, sort of a mix of familiar and more exotic molecules.
Okay, moving on from the basics then. Let's talk about the different kinds of these building blocks, the organogelators. Are they all sort of similar, or is there a lot of variety?
Oh, there's a huge variety. One way to think about them broadly is whether or not they form hydrogen bonds.
Hydrogen bonds, like tiny molecular magnets.
Kind of, yeah. They help hold things together. So some gelators don't use hydrogen bonds, think certain anthocene or anthropino types, or some steroid-based ones.
Okay, and then the ones that do use hydrogen bonds.
Those often come from things like amino acids, or they have specific chemical groups like amide and urea moieties. Even carbohydrates can get in on the act.
Wow.
The sheer range just shows how versatile these gel systems can really be.
It really does. Are there any specific types that are particularly interesting or worth highlighting?
Definitely. For instance, there are these things called 4-tert-butyl-1-aryl cyclohexanol derivatives. Bit of a mouthful. But their specific 3D shape, like whether a certain bit called a phenyl group sticks out in an axial way, that really dictates how well they form gels.
So a tiny little tweak in the shape changes everything.
Pretty much. And what's also interesting is the type of oily solvent you use with them can change how the gel looks. It can be totally clear or kind of cloudy or turbid.
And how does that affect their usefulness? Does it matter if it's clear or cloudy?
It can, yeah. This ability to control the appearance means scientists can fine-tune the gel. Maybe you want a transparent gel for, say, a cosmetic product where looks matter.
Right.
Or maybe you need an opaque one where clarity isn't important, but you need maximum stability for, I don't know, a topical medicine.
Fascinating. Okay, what about polymer organodulators? I heard they can make gels happen at really tiny concentrations.
They can, yeah. And you can tailor their gelling power by tweaking their chemical structure. Now, they might have a lower gel-to-sol transition temp, meaning they melt at lower heat,
Okay.
but they often make stronger gels compared to the low molecular weight ones we'll talk about. So strong, even if they melt a bit easier.
Interesting trade-off. Then we have Gemini organodulators. Gemini means twins, right? Does that relate to their structure?
Spot on. It refers to their twin-like molecular structure. The L-lysine-based ones are especially interesting
Why is that?
because they're really good at immobilizing a whole range of different oily solvents. They're complex molecules, sure, but the key is that this unique twin design makes them incredibly effective at trapping liquids.
Clever.
Yeah.
Okay, and finally, low molecular weight organodulators, LMWs.
Yep, LMWs, things like fatty acids and alkanes, these guys can immobilize opolar solvents even when you use them at concentrations below 2%. Really potent stuff.
Wow, under 2%, that's amazing. What kind of structures do these super efficient ones form?
They tend to form two main types of matrices, sort of different scaffolding patterns. One is a solid fiber matrix that forms when you cool the mixture down. You get these highly ordered structures, really good mechanical properties. Think of a fairly rigid, stable gel.
Right. And the other type?
The other is a fluid fiber matrix. This one forms when you add a bit of a polar solvent, like water, to molecules called amphipaths.
Amphipaths. Those are the ones with a split personality. One
Yeah.
end likes water, one likes oil.
Exactly. And adding that polar solvent makes them form these tangled up tubular structures called reverse micelles. It's a more dynamic, fluid-like network.
So depending on what you need the gel for, you might choose the sort of harder solid fiber or the softer fluid fiber scaffold.
Yeah.
Does that change how a drug might be released?
Precisely. A solid fiber matrix, being more rigid, might be great for a really slow, sustained release. It offers more strength. A fluid fiber matrix, being more dynamic, might allow for different kinds of interactions, maybe a faster release if the conditions change. It gives you options.
Now, let's talk properties. What really makes these organogels special? What's the first thing that jumps out?
I'd say their viscoelasticity.
Viscoelasticity. Okay, break that down.
It means they have this dual nature. They behave a bit like a thick liquid, that's the viscous part, and a bit like a solid, that's the elastic part. So at rest, or under low stress, they act like a solid, they hold their shape. But if you push or spread them hard enough, apply enough shear stress, you disrupt those physical networks.
And they start to flow?
And they start to flow, exactly.
That seems like a massive advantage for something you want to rub on your skin or maybe even inject. It stays put in the tube but then spreads easily when you apply it.
Absolutely. And a great example is lecithin. If you take a lecithin solution and add just trace amounts of water, the viscosity can shoot up by like 10,000 times, even up to 1,000,000 times.
Oh, just from a tiny bit of water.
Yeah, it's all down to that incredible entanglement you get in the fluid fiber matrix. It just shows how sensitive and adaptable they can be.
Amazing. Okay, so we talked about their stability earlier, that thermodynamic stability. That's a big plus. What about the heating and cooling thing again?
Right, the thermoversibility, that ability to go from gel to sol, liquid with heat, and back again when cooled.
Yeah.
That's a direct result of how those gelators self-assemble. It lowers the whole system's free energy, which is what makes them so thermostable in the first place.
So it's all connected.
Exactly. And that thermostability is why they're so good for things like drug delivery or cosmetics, where you need that long shelf life, maybe through different temperatures during shipping or storage.
Makes sense. You need the product to be reliable when you finally use it. And visually, you mentioned they can look different, clear or opaque.
Yep. Depends on the specific ingredients. Lecithin organogels, for example, are often transparent. Others, like those made with sorbitan monostearate, tend to be opaque.
So formulators can choose based on whether looks matter or if opacity is fine.
Precisely. Another tool in the toolbox.
Okay, now here's something that sounded really intriguing. Chirality effects. First off, for anyone listening, what does chiral mean here?
Chirality is basically about handedness at the molecular level. Think of your hands, they're mirror images, but you can't perfectly stack one on top of the other.
Right, they're non-superimposable mirror images.
Exactly. So if a low molecular weight gelator molecule has this handedness, this chiral center, it significantly affects how those solid fiber networks grow and how stable they are. It also impacts their thermoreversibility.
How does it make them more stable?
It allows for more compact, efficient packing of the molecules in the network. This tight packing gives them extra thermodynamic and kinetic stability. Basically, their inherent shape makes them build stronger, more stable gels.
That's really clever, using molecular shape for better performance. And finally, a really crucial one for medicine: biocompatibility. Were there issues with this in the past?
There were, yeah. Historically, some early organogels used components that weren't exactly body-friendly. That limited their use in medicine quite a bit.
But that's changed.
Dramatically. Recent research has really shifted focus towards using biocompatible ingredients, stuff that's safe and plays well with our biological systems.
And that's opened doors.
Oh, huge doors. It's really what's allowing these things to move from interesting lab concepts towards real-world biomedical applications. It's a game changer.
Absolutely. So let's talk real world then. How do these concepts translate into actual formulations? What are some key examples?
Okay, yeah. Let's start with lecithin organogels.
Yeah.
These were first described back in '88. They come from natural lecithin.
And their key features.
Well, they tick a lot of boxes.
Of course.
Thermodynamically stable, thermoreversible. They tend to melt around 40 degrees C, body temperature-ish.
Convenient.
Transparent, viscoelastic, and crucially, biocompatible and non-irritant.
Nice. And they can hold different molecules inside them.
Yeah, their structure lets them either dissolve or just kind of accommodate various guest molecules. This makes them super versatile for controlled delivery.
What's the main advantage of this specific type? Like, what problem does it solve best?
I'd say their unique mix of stability, being clear, and being gentle on the body makes them great for delivering lots of different compounds, especially where you need something that looks good cosmetically or is used on sensitive skin.
Okay. Building on that, there's pluronic lecithin organogel, or PLO. What's the deal with PLO?
Right, PLO. It's based on soy lecithin, but it also includes other things like isopropyl palmitate or myristate, water, and something called pluronic F127.
And what's it like?
Physically, it's usually a yellow, odorless, opaque gel, and it absorbs pretty quickly into the skin.
What makes it effective?
Its big strength is that it works for both hydrophobic oil-loving and hydrophilic water-loving molecules. That makes it incredibly adaptable for different types of drugs you might want to deliver through the skin, topically or transdermally.
Very versatile.
Yeah.
Then there are premium lecithin organogels, PRLOs, second generation, you said. How are they better?
Yeah, PRLOs. They offer even better thermostability, and they feel less greasy, less tacky on the skin. That's a big deal for patients actually wanting to use the product.
Definitely. Comfort matters.
And importantly, they don't contain those fluoronic derivatives, which for some people with sensitive skin can cause a bit of irritation.
Ah, okay, so potentially gentler too.
Exactly. They're often marketed as ready-to-use bases for intradermal delivery, getting drugs just under the skin, and they've shown good results in boosting the bioavailability of drugs like diclofenac, ibuprofen, ketoprofen, even progesterone when applied topically.
So more user-friendly, stable, effective. Sounds like progress. What about this Limone GP1PG organogel? Limone. That's citrusy, right. But it does something else here.
It does. Limone acts as a penetration enhancer. Think of it as a chemical key that helps unlock pathways in the skin so drugs can get through better.
Okay. And the GP1 part.
GP1 is the gelator dibutyroyal glutamide. It's amino acid type, forms a solid fiber matrix using hydrogen bonds.
So how does the Limone fit in?
Well, the Limone changes the gel's slow properties a bit, but crucially, it doesn't mess with the chemical stability. The end result is that it improves how quickly and effectively the active drug can permeate through the skin. It helps the medicine get where it needs to go faster.
Smart combination. Okay, next up, gelatin-stabilized microemulsion-based organogels, MBGs. Gelatin's a protein. You wouldn't necessarily expect it to mix well with oil-based systems.
Right, you might expect phase separation, but surprisingly, you can use gelatin to form these transparent gels with water and oil microemulsions.
And what's their unique selling point?
What's really cool about MBGs is their electroactive nature.
Electroactive.
Yeah, they respond to electricity.
Yeah.
This makes them really well suited for something called iontophoretic delivery,
Wow.
where you use a very mild electric current to actually push the drug through the skin.
Wow.
And this leads to higher release rates, plus they seem to have better microbial resistance. It's very powerful for targeted, enhanced delivery.
Very cool. Then we have fatty acid-derived sorbitan organogels, using things like sorbitan monostearate.
Yep. These are hydrophobic, non-ionic molecules. They're good at immobilizing various solvents.
And how do they form the gel? It sounded interesting.
It is quite neat. They form solid fiber matrices, but the process involves these tiny sort of donut-shaped structures, toroidal reverse micelles, which reorganize and basically unspool into rod-shaped tubules. These tubules then tangle up to form the gel network.
Huh. Like microscopic spaghetti tangling up?
Kind of. They're usually opaque, thermoreversible, and pretty stable at room temperature for weeks.
Okay. And lastly, polyethylene organogels.
Right. These are typically colorless gels. You make them by dissolving low molecular weight polyethylene in something like mineral oil at high temperatures, then cooling it down really fast, shock cooling.
And where are these used?
These have actually been used extensively for a long time as pretty standard ointment bases, a stable, common platform for many topical creams and ointments you might already know.
Okay, so we've covered a lot of different types and properties. Where do organogels really make their mark? What's the main event when it comes to applications?
Drug delivery. That's really where the excitement has been building. Since they were first described in '88, interest has just grown exponentially.
Why the surge in interest?
It comes down to that great combination of factors. Longer shelf life, they're often easy to prepare, that useful thermoreversibility, and their amazing ability to carry both water-loving and oil-loving compounds.
Right, that hydrophobic versatility.
Exactly. It means they can potentially carry a huge range of different medications for all sorts of purposes.
Makes sense. So let's talk delivery routes. What about parenteral delivery injections? How are organogels used there?
Well, some, like those sorbitan monosteroid organogels, have shown promise. They might have a relatively short half-life right at the injection site, but they have been used successfully for sustained delivery of antigens.
Antigens, like in vaccines.
Exactly. Where you might want a slow, steady release over time to stimulate the immune system, that's incredibly valuable.
And there are even more advanced injectable systems.
Oh, yes. There are L-alanine-based injectable organogels that actually form in situ, meaning the gel forms after injection inside the body.
Whoa.
These are being developed for sustained release of really sensitive large molecules, macromolecular agents like leuprolide, for example.
And how long can they last?
We're talking potentially 14 to 25 days from a single injection. And they've shown good biocompatibility in tests.
A single injection lasting for weeks? That would be transformative for patients needing regular shots.
Absolutely. Huge implications for compliance, convenience, and there are even thermosensitive polymer organogels being designed.
Thermosensitive?
Yeah, engineered to release their drug cargo specifically when the temperature goes above, say, 40 degrees C. So you could have release triggered by fever or localized heating. Truly targeted release right inside the body.
Incredible potential. Okay, what about oral delivery? Taking them by mouth. You mentioned that's less explored.
That's right. The source material we looked at had fewer reported examples for oral use. But the ones mentioned are pretty interesting.
Like what?
There was a study back in 2005. They gave cyclosporine A, which is an immunosuppressant drug, to beagle dogs. And when it was delivered orally in a sorbitan monolith-based organogel, it showed improved activity compared to other forms.
Promising. Anything else?
Another study used 12 hydroxysteric acid organogels containing ibuprofen. This was tested in rats for controlled oral delivery of lipophilic or oil-loving compounds.
So while it's maybe early days for oral, there's definitely potential there too, especially maybe for drugs that are tricky to deliver normally.
Exactly. But really, where organogels have made the biggest splash so far is in topical and transdermal delivery, applying them to the skin.
Right.
Lecithin-based organogels, for example.
Right.
We know they have proven long-term biocompatibility, low irritation, ideal for skin applications.
And they're not just for like moisturizing or simple pain relief, are they? I read they can significantly improve the transport of some pretty complex molecules.
Absolutely. We're talking diverse bioactive agents, things like complex aromatic tetraamidines, amino acids, even peptides. Getting those through the skin effectively is a big challenge.
And they've even shown success in animal models against tumor cells.
Yes, in some experimental models, applying organogel formulations directly to the skin has shown success in reducing tumor cell growth. That's a huge potential step forward for topical cancer therapies, though still early.
Wow. That's powerful.
It really is. And remember those penetration enhancers we talked about.
Like limon?
Exactly. Or other terpenes like linalool, cineol, farnesol. Adding those into the organogel formulation can significantly boost how well the active drug gets through the skin barrier.
So you can stack the benefits, the gel structure plus the enhancer.
Precisely. And let's not forget those gelatin-containing MBGs we discussed.
The electroactive ones.
Yep, their suitability for iontophoresis using that mild electric current.
Right, to push the drug in.
That enhances delivery even further. You get higher release rates, better microbial resistance. It's a really sophisticated approach.
And have specific drugs been delivered this way successfully?
Yes, examples like methylnicotinate, indomethacin, diclofenac, common anti-inflammatories or circulation boosters, have all been successfully delivered topically using these advanced organogel systems, sometimes combined with iontophoresis.
Okay, so wrapping this deep dive up, it seems organogels offer this really immense potential. They're versatile, stable, often biocompatible systems for getting drugs where they need to go through various routes, injection, maybe oral, and definitely through the skin.
Yeah, they're like these incredibly smart, tiny delivery vehicles for medicines, designed to be precise, stable, and effective.
And the future looks pretty bright.
Incredibly exciting, I'd say. Once their full biocompatibility is even more firmly established across different types, you can see these self-assembled structures really taking off.
Where?
In pharmaceuticals, definitely, but also maybe in nutraceuticals delivering vitamins or supplements. They could potentially replace a lot of conventional ways we formulate and deliver active ingredients, offering more precise, efficient alternatives.
Absolutely. It really makes you think. Imagine a future where your medications aren't just delivered, but they're intelligently released exactly when and where your body needs them, all thanks to these amazing semi-solid structures. So, here's a thought to leave you with. What other everyday products, thinking beyond medicine now, could be completely revolutionized by these smart gels?